Welcome. In this session, we'll explore convexity. For convexity, the first thing that we'll do is we'll consider the definition of a chord. So a chord of a function f, and here we're still in scalar land, so this will be a function that has a scalar argument. A chord, let's put this in quotes because it's colloquial. This connects 2 points of the function. And let's take an example. Let's suppose that this is our argument, t, and this is our function, f of t. And let's suppose that we have a point t1 and a second point t2. If we evaluate f at t1, we'll get something here. And that will have coordinates in the plane t1 and f of t1. And if we evaluate it here, it will have coordinates which are t2 and f evaluated at t2. And we connect these with a line segment. So our assumption immediately here is that t1 and t2 are distinct. What we would like to do is, let's suppose that we take a step along this. So we'll take a step of amount theta. So we'll use a parameter theta, and if we take a step theta here, then that will give us a value. And if we take going between here and here, so this will be f evaluated at t1, this will be f evaluated at t2. If we take a step that goes amount theta between these two, so if this step is also theta, then that will match and we will have an interpolation. And if a routine thing that we do is we'll say that theta varies from 0 to 1. So when theta equals 0, that will evaluate to t1. And when theta equals 1, it will evaluate to t2. And what we would like to do is then be able to take these steps along, and as we do so, we're basically moving a 2D point from this first location to this second location. So that's the idea of interpolation. And the question we would like to answer is, if we now have a function, for example, if we have a function that is like this, we can observe that if this function is convex in this domain, then that function's value is always underneath the chord. So geometrically, if the function lies underneath the chord, then the function is convex between these two endpoints. And if it is entirely above, it would be concave. That's not so interesting to us. And the danger situation is if the function is non-convex, that is, if it goes below the chord and above the chord on that interval. We're only interested in the convex case. Now, let's define a strictly convex function with reference to this. So a strictly convex function is one of the two kinds that we'll deal with a lot here. And the definition is for any first point that is a real number, and for any second point that is a real number, and for any parameter that is, here we're going to be specific, it's not just non-negative, it's a positive number such that it's strictly less than 1. So we can say for any real theta such that theta is strictly between 0 and 1, we'll say that f is a strictly convex function. Function is defined as, and now we'll formally state this geometry here. So if T1 and T2 are not the same point, and 0 is strictly less than theta is strictly less than 1, then what we mean is, if we evaluate the function at this theta, so what does it mean to be evaluated at that theta? Well, what that means is, if we take T1 times 1 minus theta and add theta times T2, let's see what that would do. If theta was exactly equal to 0, this would evaluate to T1, this would evaluate to 0. If theta was exactly equal to 1, this would evaluate to 0 times T1 plus 1 times T2 to T2. So this is linearly interpolating. Those would be the boundary cases that we can't apply here, but our reasoning is that this linear interpolation will take us between T1 and T2 as we increase theta from 0 up to 1. And if we evaluate the function at that point, then it has to be strictly less than this interpolant. So that means it has to be strictly less than, well, what would that interpolant be? That would be, if we evaluate the function at T1 and we multiply that by 1 minus theta, and if we then evaluate this function at T2, so that's giving us this value here, and we add theta times that, that would linearly interpolate these. So if the function evaluated at this intermediate value is less than the interpolation between f at T1 and f at T2, then that means that this function is strictly convex on that domain. If we have a convex function, so convex function, what we do is we will modify that, and you can see the notes to get the formal definition. We allow 0 less than or equal to theta less than or equal to 1. That is, we'll now relax this condition and we'll allow theta to actually be at T1 and at T2. And then we'll replace the strict inequality with an inequality. And if we do that, we'll have a convex function. A strictly convex function is a particularly nice function, but it's one that we often won't have. Usually what we end up analyzing in this course is a convex function.